Okay, welcome to the first lecture of statics, and today we're going to be talking about scalars and vectors. And I have three objectives for today. One, I want to review Newton's laws. Two, I want to define vectors and scalars. And then three, we're going to do some math on vectors. Some of this, for some of you guys, may be a review. I don't really know for sure. You should have seen some of this, and a lot of this, especially Newton's laws in physics. But we're just going to go ahead and make sure we're all on the same page. Before we get into this, I do want to talk about one particular thing, just to kind of, because this is the beginning of statics and we're kind of like on our way there. So I'm just going to kind of just very briefly, because I think that this is going to help us kind of place us, where we are in the larger scientific world. So the largest world here would be just called mechanics, right? And so mechanics is basically applied math, dealing with kind of macroscopic. So we're not dealing with molecules and things like that. Dealing with motion and forces and, macroscopic objects. Okay, and this typically can be split up into kind of three directions. So one would be rigid bodies, one would be, deformable bodies. And I think you're going to get into that eventually, okay? And then the third one is going to be fluid mechanics, okay? And, some of you guys will have me in fluid mechanics. Some of you will avoid that. Hopefully, as this class is not such a bad experience that you guys hate fluids, but you can picture a fluid as it's not even really, well, it's a body, but very deformable and it can actually flow. So these things can actually flow. These things can deform, which means if you got some forces on them, they can, they can bend, or they can, if I drew a box or something and I were to push here and push here, you can imagine that this thing would kind of go into this shape right here, just because it's responding to the stress. What we're going to be dealing with in this class is going to be rigid bodies, okay? And this is going to show up in a few different ways. Most notably in the way that what I've just drawn right here, we're not concerned with the deformation. We're concerned about the fact that this object, if it had a force right here and a force right here, would tend to spin. Okay, so that would concern us. Okay, but we wouldn't be worried about the deformation of the object. Okay, so we're going to treat it as if these objects are rigid. Okay, and that's going to show up in a lot of different ways, and we'll kind of talk about that as we go. But like right here, rigid bodies basically can get split up into statics. Okay, and that's what this class is in dynamics. Now, dynamics has a cooler name, and in some ways it is cooler. But you can't do statics. You can't do dynamics until you've done statics. And statics, dynamics is, in this university, it is the hardest course. Okay, and it wouldn't surprise me if that's kind of the way it always is. But basically the difference between these two is that in statics, the sum of the forces equals mass times acceleration equals 0. Whereas over here in dynamics, the sum of the force, well, that's not really what I wanted. The sum of the forces does not equal 0, okay? Now, we could also say the same for the moments over here too, and moments is basically you can think of it as torque, or basically the propensity for things to spin. Okay, and so dynamics is in some ways more interesting because things are moving, but actually in statics, and this is important, we need to make note of the fact that this 0 means the acceleration is 0. So what we're talking about here is things that are at equilibrium, where equilibrium means the acceleration is 0. Okay, it does not mean the velocity is 0, just the acceleration is 0. Okay, now almost all of the statics problems have to do with things that are not moving, or at least not moving relative to whatever your reference plane is. But sometimes all of these laws will work for things that move. That move but have a constant velocity. Okay, so the key is really just that the acceleration is 0. Okay, from there, and just to kind of finish up kind of like a really quick intro. Since we're in mechanics, there's a really important thing that we must always consider when in any kind of science is we must consider the units that are going to pop up and kind of the metrics that we're typically going to run across, okay? And the nice thing about classes in mechanics is that we don't really have a lot of weird units. We're not going to be dealing with BTUs or joules. Those would be for energy. I guess we will end up with some energy here and there. But for the most part, okay, most things are going to be lengths. Well, I guess we don't need the S there, but lengths. We'll just turn that into a colon or something. Length, mass, okay, time, force, and we'll go ahead and put work in there and power, okay. And this is kind of the gist of what we're going to run across, and we must remember that there's two systems: the SI system and the English system. I have no idea actually what your book calls this one. We'll just call it English for now, although ultimately it's really the American system because we're the only ones foolish enough to continue to use it. And the standard unit for the SI is, of course, meters, and for English it is feet. For mass, it is a kilogram, and for English it is the slug. Okay, I will make a very important point. It is not the pound mass. A lot of people like to use that. That is a horrible unit. And I will explain why in a second. Okay, so time is the same for both. It's seconds. Obviously, you can use other units. Like you could use hours if you wanted to. But, we're not really going to do that. So, I guess sometimes you will. You'll start with, miles per hour or kilometers per hour, and you want to kind of use that. And from these, okay, we get these other units, and these are fancy units because these are what we call derived units. Okay, so derived units. And these guys, they're combinations of the other units. Okay, and I can't stress enough how important it is to remember this because it will make your life a lot easier. So I'm going to add two more down here, velocity and acceleration, because I think these will make it clearer what a derived unit is. Okay, so velocity is a meter per second. Okay, and so it is a combination of two of the units from above. Okay, so for the English, it's foot per second. Okay, now obviously you could do miles per second or miles per hour or whatever. You can use other units, but these are the standard units. And usually your life's going to be a lot easier if you use the standard units. Acceleration is meters per second. So that means something is changing by a certain number of meters per second, which we typically write as meters per second squared. Okay, and then for the English units, we use feet per second squared. So that's feet per second. Okay, so if something's accelerating 32.2 feet per second, that means every second it's going 32.2 feet per second faster than the previous second. Okay, now force is not so easy as that, but force, and I highly recommend you always remember these. Force is, really it's the sum of forces equals mass times acceleration. Okay, we're going to put our little vector arrows on there, which we're going to talk about in a second. But mass is measured in terms of, let's say, kilograms. And acceleration is measured in terms of meters per second squared. So force is measured in kilograms times meters per second squared, which we call a Newton. Okay? And that is always true. Okay? And this is why it's nice if you have the standard units, because if you plug in kilograms right here, if you plug in meters here and seconds squared here, then what comes out the other side is going to be a Newton. Okay? Similarly, if you use the standard units and you plug in, let's do the English units, if you plug in a slug, foot, per second squared, you're going to get the standard unit over here, which is a pound. Okay, so we're going to get slug times feet per second squared equals 1 pound. Okay. Now, a lot of times as you get into engineering, people will write it like this. So you might know that pound sign from your phone. And we like that sign, right? 1 pound from your phone. Okay. It's just to save energy. Sometimes you will also see, just because it makes our lives easier, like for newtons, you will see all the SI, subscripts that come with that. You might see a meganewton or kilonewton or whatever. And a lot of times for this guy right here, you will see like 1K or 1 kip, okay, which is a kilopound. So it's 1,000 pounds. Okay, so basically they kind of stole the prefix idea from the from the SI system. Okay, there's no problem with that. It's just the way it is. All right, now work. If you remember from wherever you took physics, you might remember. I'm going to kind of give myself a little space over here, but for work, work equals force times distance. Okay, roughly. Okay, and this has a direction, and this has a direction. And work is, in this case, this is a dot product, so work is a scalar. But from a unit standpoint, work is kilograms meters per second squared times a distance, which is a meters. So kilograms meter squared second squared. Okay, kilograms meter squared second squared, all of which is 1 joule. Okay, and typically we actually write this as a newton times a meter. Okay, but it's important to be able to get back to this. Okay, because there'll be times where you're like working through your units and you've got a pile of units and you go, oh look, kilograms meter squared second squared, that's a joule, and you're able to just write J instead of all this all this mess, because nobody wants that mess. Okay, similarly. Energy on the English system is usually it's written as a foot-pound and not a pound-foot, but you could write it as a foot-pound, pound-foot. They don't have a special name for it. Sometimes you might see a BTU, okay, but don't use a BTU, okay? That's a British thermal unit, and it's primarily used, obviously, in heating and cooling, otherwise, hence the thermal in its name. We don't really want to play with BTUs, okay? That really stinks. Okay, and if you remember then also from wherever you took physics, that, so if we take that one step forward, so now we remember power, and power is the rate at which work is done, so it's work divided by time. Okay, so now I've got, if I wanted to break it all the way down, that's joules per second. And I don't know where that symbol came from. And a joule, of course, is a kilogram times meters squared per second squared. And now we, take that second from the bottom and put it there. And so now we've got kilograms meters squared seconds cubed. And that is a watt. Okay. In a most annoying fashion, I'm going to put these square brackets on there so you know that this means the unit and not the quantity work. Okay. So power is measured in watts, which is joules per second. Okay. And similarly, power for the English system is foot-pounds per second. And sometimes, okay, and this is not necessarily standard, but sometimes it can be measured in horsepowers. And so it will be 550 foot-pounds per second equals 1 horsepower. Okay, so if ever you want to make that if you ever want to make that conversion, you may. Okay, I don't really recommend that either. Units are kind of messy and kind of cool, but they are what they are. Okay, so I would recommend actually taking this like chart or whatever and putting it somewhere where you can find it. Okay, this will help you on a test or a quiz or anything. It'll help you throughout your engineering career. And what I would do is I would leave space down here for other quantities. Okay, I mean I would almost like, I guess if you knew that these were all of the ones you were going to have, I would laminate it. This is going to show up so many times, so often, and if you're you're going to have so many classes, and they're going to throw so many of these things at you, and there'll probably be more of these in this class, but these are the basic ones. okay? And they're just going to keep coming, okay? When you have to take, for example, fluid mechanics, now you've got the viscosity of the fluid, and you've got, you know, densities and things like that. And all of these things are just combinations of these units. Okay, so last thing before we step forward, and I'm going to add one thing to my chart over here just because I forgot it, and we're about to step into it, is I want to make a very clear distinction here. This is for Newtonian mechanics, okay? I'm not going to worry about Einsteinian. I'm not going to do relativity. I don't understand relativity. I read about it. It's fascinating. It's really cool. I hope you guys get interested in it. But there's just flat out, it just doesn't have anything to do with engineering, right? Or just general engineering. If you're going to go be an aerospace, not aerospace, if you're going to somehow work on, you know, work on the stars, then it will start to really, really affect things. At this point, there's so many sources of error that are much bigger than the fact that we're not dealing with, you know, that we're not using Einsteinian's equations, we're using Newtonian's equations. Okay, so let's get Newton's laws, and we'll just, Newton's laws. Okay, and so you've heard these before almost certainly, but we'll just go ahead and do them again. You may not remember which was which. I suppose it's not really that important, although, you know, it's probably a nice thing to have in your back pocket. I'm going to go ahead and write these out, you know, as they are commonly are. Okay, so there they are. And if you want to, you can pause the video if you want to spend a little time copying it down. But, you know, I'm going to talk about these one at a time, and I'm going to start with the second law because the second law to me is the greatest of all of them. And really the first and the second law to me are the same law in a lot of ways. And I will kind of talk about these wordings and how I like them and don't like them. Okay, so the force acting on an object is equal to the mass of the object times the acceleration. So you know this from high school as force equals mass, or maybe not high school if you didn't have physics in high school, but you know it from physics as force equals mass times acceleration. Okay, this is incomplete in my opinion. Really, it needs to be like this because force is a vector, which we're going to talk about in a second. Acceleration is a vector. And really, it should have a summation symbol right there. And so, because if you have two forces and they're equal and opposite on something, it's not going to accelerate. You know, if you've got one force pushing on something with, you know, 10 newtons from the right and one, you know, 10 newtons from the left, they're going to balance each other out and there's going to be no movement. Or no acceleration, okay? There could be movement, but there doesn't have to be acceleration. Okay, and so that, to me, this is the most powerful of Newton's laws. Okay, and they all kind of are powerful. This next one, okay, we're going to go back to the first law. This is the most important one for statics, is a body at rest will remain at rest, and a body in motion will remain in motion, comma, unless it is acted upon by an outside force. And again, I don't like this. To me, there needs to be like, unless there is a force imbalance, an outside force imbalance. So we would write this as sum of the forces equals 0. Okay, so if the sum of forces equals 0, then A equals 0. Okay, so where acceleration, because it's a scalar, so basically anything, I mean, because it's a vector and it includes, well, we haven't talked about vectors, but basically any acceleration is any change in velocity. So if you change your direction, if you change your speed, then you've accelerated. So then basically this right here is just a special case of this. Okay, so if the sum of the forces equals 0, then there's no acceleration. Okay, then the direction won't change and the velocity won't change. Okay, so this first law is where we are in statics, okay, because we are going to be dealing with things that do not accelerate. Okay, this one right here, this is dynamics. Okay, which in some ways should make you feel a little bit better about dynamics. If you can do statics, and you can, you know, we just got to work at it because you haven't seen it yet, then you should be able to do dynamics. Because look, it's just one extra step. It's this step right here. Okay? Okay, and the last one is, for every action, there's an equal and opposite reaction. Okay, and I'm going to I want to talk about all of these in terms of, fairly simple, thought experiment, just because it's, we can all see this. I have this right in front of me. In fact, I'm sitting at a desk in my living room because there is a pandemic going on. And you imagine there's a book sitting on top of that desk. Okay, so there's the book. All right, so we're just going to think about the book. So the first thing that I want to do here, before I think about this book in any further way, is that we want to think about just the book. So I'm only going to draw the book. So this is called a free body diagram. I'm going to try to make sure that I do one of these in every single class. And what you do when you draw the free body diagram is I'm just going to draw the book. Okay, so here's the book, and here's the pages. You know, whatever. It's a terrible book, but you know what do I know? So it's got a bunch of pages along here, and whatever. It's a book. Okay. Now, when we draw free body diagrams, we just draw the object, and then we immediately want to think about the forces on it. Okay. And so there's basically going to be a few different types of force, and there's what we call body forces, and there's surface forces. Okay. And so the way that we think about this when we do this is you're going to do these forces in terms of, so the body forces is basically is gravity. Okay, so you have to ask yourself, is there gravity acting on this particular book? And in this case, yeah, there's gravity acting on this book. Okay, so what are we going to do? And we say, well, what direction is it? It's acting downwards. Okay, so typically there's two ways to refer to gravity. You can either call it F sub g for the force of gravity, or weight. Okay, I kind of prefer weight. And that's a vector, so we'll put the little arrow on top. Okay, so it's a downward vector. So the body force is weight. Okay, in fact, it's the only body force that I can imagine. Well, not really. I mean, there's things like magnetism, and I'm sure if you got small enough, you could start thinking about other forces. But for us, it's just going to be body. That's the only body force we're going to worry about. Okay, surface forces, and the way that we look for those is we think, basically we're going to almost like trace the outline of this book, and we're going to think about what's touching it. Okay, just the surface. Okay, and everywhere where something is touching it, we didn't draw that, but we have to draw the effect of that. Okay, and so the most obvious thing is all along this bottom edge, okay, it's touching the table. Okay, and so the table is going to be pushing up this way, okay, with the normal force. Okay, and this is typically written as F sub n for normal, or sometimes it's written as the normal force, like that. Okay, now we have to think about these other surfaces. So we've got a surface here, and we've got a surface here, and all the way around here. And so when you get to those, you have to ask yourself, are we concerned with air pressure? Okay, because air is touching it, it's pushing on it. Are we concerned with that? Okay, and in this class, no, we're not concerned about that. Okay, so you can just ignore air pressure for this class. Okay, so what's going on here? Okay, so now we have to think about these things. And so if I wanted to quantify this normal force, well, we can do this with Newton's laws. Okay, so for every action, there's an equal and opposite reaction. So this weight force is pushing downwards, basically on the table. And so the table is pushing back with the normal force into the book. Okay, so these two are equal and opposite. So I know that at least in terms of magnitude, that these two are equal. Okay. Now, I also could have gotten that from the first law, okay, where I know that this book is not accelerating. Okay, this acceleration equals 0. Okay, so what does that mean? Well, that means the sum of the forces is equal to 0. And how does that happen? Well, that happens because the normal force, which is going upwards, is equal and opposite to the weight. Okay? And that's the gist of Newton's laws. And we're going to be talking through these constantly. Again, I would write down Newton's laws, and I would, I'll write them down on the front of your, your binder or something, and just kind of always have them there. But we're going to do this again and again and again. And what is key to me is this. You have to be able to draw a free body diagram, which means you're going to have to be able to think about body forces and surface forces. Okay, and I'm gonna draw so many free body diagrams. I'm trying to make a point to always have at least one in every lecture. Certainly there'll be one in just about every homework, so that's important. And then the other thing is to kind of talk through these laws. Okay, they're gonna pop up again and again, but really the most important thing in this course is going to be this. Okay, and identifying when there's a reaction force. Okay, so with that said and done, let's we're 25 minutes into this class, and let's go on to some vector math. Okay, so we're going to go over here, pick a nice spot, and we'll talk about scalars and vectors. Okay, and so the first thing we want to talk about is a scalar. So a scalar is a quantity represented, I kind of hate this way of saying it, by magnitude alone. Okay, so that's kind of a silly, it's basically a way of saying it's a quantity that doesn't have a direction. So these are things that are, measured, they don't have a direction. So if I said, what is your mass? You would say, well, I'm, 20 kilograms. You wouldn't say I'm 20 kilograms to the left. You wouldn't say, if I said, what's the temperature outside? You would say it's, I don't know, today it's probably like 77 degrees Fahrenheit, not 77 degrees Fahrenheit in a direction, just that idea, okay? And the vector is the opposite, or maybe not the opposite, but it is a quantity that has magnitude and direction. Okay, and so that's important. And typically, the easiest things to think about for this is force. Okay, and we put a little arrow over it to show that it has a direction. Okay, velocity has a direction. Acceleration has a direction. Displacement, so sometimes that can be x. Doesn't have to be x, it could be y or z, depending on, sometimes x just means position in general. Whereas, the scalars, typically you might have mass, or you might have work as a scalar. You might have, I mentioned temperature, but you don't put a little arrow over the top. Okay, so like in our little, so if I wanted to draw a scalar, there really isn't really a good way to draw it. So if I wanted to draw a mass, well, here, I don't know, maybe that's a mass, I don't know. And I might just like kind of say, well, that's 10 kilograms. Okay, that certainly would be acceptable. If I wanted to draw work, I don't really know how I would draw work. If I wanted to draw the temperature of this thing, maybe I would just put a thermometer coming off the top and, draw some, something like that. But I'm not really, it doesn't really have a direction. It's not actually going up to the left and, up and to the left. It's just, it doesn't have a direction, okay? If I wanted to draw force, on the other hand, the way we always draw these is it's got a, we're just going to draw an arrow. And the arrow is the magnitude, okay? So this right here, the length of the arrow, that's the magnitude of a vector. Okay, and then this is the direction of the vector. Okay, so usually you give it an angle. It can be a theta. It can be whatever it is. Whatever you want to do. So that is the direction of the vector. Okay, now what is common here? So I don't know what I want to call this vector. Let's call this vector A or something. Maybe not A. Let's call it capital A. So it's not acceleration. It's just a random vector that I've drawn here. And what's typical is right here, we would draw, this is the magnitude of the vector. So you kind of draw these absolute value signs around it. It indicates that we've gotten rid of any kind of directions, which is, of course, exactly what an absolute value sign does. And then the direction of the vector is often written kind of with an angle sign. Okay, so this is pretty common. I will note that your book is a little bit different. So if I do the book, then what they would do instead is for this, is that basically, so the quantity of the vector is just the letter A. Excuse me, the magnitude of the vector is just the letter A. The direction is drawn something like this, so that's okay. But then the vector itself doesn't have an arrow. Okay, it's written in bold. Okay, I can't draw in bold on this. Okay, so I'm going to use these little arrows. Okay, but your textbook is going to have a bolded F. Okay, so if I could draw in bold, it would look something like, I don't know, this. Regardless, I don't have the time or the patience to draw these F's in bold or these velocities in bold. Not to mention it wouldn't even be that clear necessarily when I was doing it in bold. So we're just going to use a little arrow on top, and I think that you're just going to have to mentally change from one to the other. Okay, so that said, now we need to start thinking about vector math. Okay, so what I mean by that is we're going to talk about some basic things that we can do with these, and some important things that come up. So, for example, if I had a scalar quantity, let's just kind of define some quantities to play with. Okay, so I'm going to say I've got a vector that looks like this. That'll be A. Okay, I've got another one, let's say, going like that. That's B. Okay, I've got a scalar quantity C. Okay, and we'll make another, we'll just give ourselves another scalar in case we want to play with it. Okay, and let me give a couple more. Let's give another one that goes like this. We'll call that E. And let's get an F that goes in a random direction. So let's just go like that. Okay, so we're going to play with these 6 quantities here. Okay. And the first thing that we want to do, and there's a lot of different ways that you can combine these different things. But so the first thing I want to do is I want to multiply a scalar times a vector. Okay. And what I'm going to do here, just to kind of like give us an idea here, I'm going to make C equal to, say, a half, and D equal to, say, 3. Okay. So C times A, okay, is A divided by 2. Okay, so it's half of A. Okay, so we just multiply them. Now, the thing to note here is that this is a vector. Okay, and what this would look like is it's going to be, if this is the original A, like that, then A divided by 2, okay, well, obviously I can't draw, but A divided by 2 is just going to be half as long. Okay, similarly, if I did D times A, I'm not going to, it would be 3 times A. Okay, so it would be, so this would be A over 2. Okay, and this would be 1, 2, 3 times as long, so that would be 3A. Okay, note it is still a vector quantity. It has magnitude and direction. It's just 3 times as long. Okay, and this actually happens to us all the time. This is a common thing. So, for example, sum of the forces equals mass times acceleration, and here we've got a scalar multiplied by a vector. Okay, notice when we multiply these two, we get a vector. Okay, so you scale the acceleration by the mass in order to get the force required to create that acceleration. Okay, so this is really, really common. It happens all the time. One of the other things you could do, I could change D. Let's suppose I made D a -3. Then D times A would, in that case, D times A would be equal to -3. Okay, and in which case I will have simply changed the direction. Okay, so -3A. Okay, so that is that's what happens when we do a scalar times times a vector. Okay, so that's scalar times vector. Okay, and that'll come up from time to time. As you can see, it just came up. Or you've probably done this before in physics class, and you didn't even give it too much thought. Okay, the next thing we might want to do is we might want to add vectors. Okay, so we're going to do addition of vectors, And there's a lot of different ways to do this, and this will probably be the remainder of this class. We're at about 35 minutes on this one. If you wanted a stopping point, this would be an okay one. Go, do some jumping jacks, scream at what a horrible person I am, what a horrible teacher, and, all the annoying noises my dog was making in the background. That would be fine. Take care of your mental health. Let's always remember that's important. It's more important than this class. Sorry, I had to drink some water. Thirsty. Okay, so if we're going to add vectors, and I guess we need to keep these kind of visible, let's suppose I did a vector A, and I wanted to add it to B. Okay, and B is, kind of short like that. Okay, well, one of the cool things about vectors is this. You can think of them almost like paths or something that you walked. Like you can think of it as like I walked in A, and then I walked back in B. And where would you end up? Well, the answer to that would be, well, you went A this way, and then you came back B. So the answer is from the initial point is to go about there. So this is B, this is A, and this is A plus B. Okay? Or another way to think about that is A is let's say positive, 7, and B is negative 3. Okay, let's make that, let's give it some units. Meters and meters. Well, you went 7 meters to the right, and then you came back 3. So A plus B then is positive 4 meters. Okay, you could do this with anything else. If you wanted to make these forces, you could make this newtons, and you could make this newtons, and you could say, well, I've got a 7 Newton force from the left, I've got a 3 Newton force from the right, and together I get a 4 Newton force. Okay? Again, that's just those are just other vectors. Okay, now obviously the problem with this notation is it doesn't really show the direction, but it does because I put a plus sign there. Okay, so you need to remember if you're not going to draw like an arrow defining the direction, you need to be very careful and make sure that you put a visible plus sign. I also highly recommend that because that reminds you that you've taken care of it, okay, that you haven't forgotten it, okay? So other ways, the other nice thing about this is that, so A plus B, in this case, equals, I'll say 4 newtons, we'll just keep it as newtons, going this way. In this case, I guess a second ago I did that incorrectly, so let's get rid of that, going this way. The other possibilities, you could say B plus A, okay, also equals 4 newtons to the right. Okay, notice it doesn't matter what order you do it. Okay, in that case, we would start at some origin. We would go B in this direction, and then we would come back A in this direction. And the total right here would be B plus A, okay, and it would be the same. So we can say that A plus B equals B plus A, okay? And that's some sort of fancy, property of math that is commutative, okay? I never remember these, if it's commutative or associative, but I had to look this one up, but in this case, that's commutative, okay? So you can add them in different orders. Now, the nice thing is that doesn't just apply to when they are, so these two, when they're collinear. So these two right here, they're special, right? They're collinear. Collinear. That means they are along the same line. Okay, so that's kind of a nice thing that kind of helps us with adding these suckers. Okay. I should note before we move away from this sort of thing that you can also subtract vectors. So I can do A minus B. Okay, and it's kind of like, well, that's kind of annoying. So how would we do that? Well, mathematically, you could do it as like, well, I'm just going to plug in A, which is a plus 7 newtons, and I'm going to plug in a B, which is a negative 3 newtons, okay, and total I'm going to get 10 newtons, okay, but graphically, what you're doing is you're saying, all right, so I've got A, which is 7 newtons to the right, okay, and now I'm going to apply a negative B. So a negative B is 3 newtons this way. Okay, so now in grand total, okay, because the positive B was actually a negative 3 newtons, so the negative B is a positive 3 newtons. So now that's going to be a positive 10 newtons. Okay, or more to the point, it's positive is 10 newtons to the right. Okay. Another way to think about this, and if we're thinking about this in newtons, is I think about it as I am removing, say a negative force, So perhaps there was a force initially that was pushing it to the left, and it's been removed. And so the net effect now is there's 3 more newtons to the right. Okay. So kind of hard to think about it that way. So let's, mathematically, it's pretty straightforward like this. The nice thing is we can say that negative b plus a equals a minus b. Okay, so basically it's, I don't know if that counts as commutative. I guess it does if we did plus negative. Okay, so let's bring in something else into this mix. So let's bring in a little, and I guess before I completely move on, we could always add in a 3 in here. So I could do like 3a plus b, right? Okay, and so you could imagine that as a times a, 3 a's, and then we're going to add a little b on the end, and of course the b is a negative 3, so it's going to kind of come back this way, right? So this is your b, and this is a. Okay, so I multiplied it by a scalar, and now I got 3 of them, and I'm going to come back b. Okay, so I'm going to go over 7, another 7, another 7, and then I'll come back 3. Okay, so we're going to end up at 18 newtons or meters or whatever it is we're measuring to the right. Okay, the nice thing here, and you could also split this apart and do a plus a plus a plus b if you wanted to. But the nice thing about this way of doing it, okay, and this is important, is that it works no matter what kind of weird directions we have. Okay, so I'm going to go ahead and delete all of this. Okay, and then we'll just zoom in, if it will let me, zoom in. Okay, so we've got these guys, these 4 random vectors I made up. Let's give them some values. Okay, so we're going to start adding kind of 3 of these, and I'm going to pause for a second and kind of draw these as best I can separate, but let's just kind of like talk about a few different possibilities. And obviously, it's actually kind of nice to look at your textbook because it's got some nice, it's got much better drawings than this. Okay, so we could do that, and we can compare that. Let's do it like this, and then we'll compare that as best I can draw to like this. Okay, so let's. Okay, so I'm going to zoom in here. Let's look at what I've done. Okay, we're trying to get at a plus b plus f, and we're going to check to see if this is associative. So what we're going to try to do, and obviously my drawings are not going to be perfect here, but the idea here is to get at, does it matter if I do a plus b first, or can I do b plus f first? So here's how we're going to do it. I'll kind of just line up what we're doing. So first we've got a. Okay, so that's a positive 7 or whatever a was. Let's kind of keep that in our vision here. Okay, so we're going to go kind of over 7. Then we're going to come back 3. Okay, and now we're at this point. Okay, so that means that this particular line right there, this particular line right here. Okay, if I highlight it, okay, that's a plus b. Then I'm going to add that quantity to quantity f, to, vector f. And vector f, of course, if we look over here, it's kind of going down and to the left. Okay, so we're going to go back this way. Okay, and now that's a plus b, and we've added f. Okay, for a net total of this line going, and obviously, we're just kind of guessing here. This isn't mathematically precise. Okay, but we're going to end up something like that. Okay, so this is a plus b plus f. Okay, when we do add a plus b first. Okay, now we're going to do this second one, and we're going to try to do it where we add b and f first. Okay, and I'll do this one live for you. So b is going to be going this way. Okay, so that's b. Okay, f is going to go back down this way. Okay, so that's f. And then we've got A, so that means that this right here, okay, that's B plus F. Okay, and then A is to the right this way. Okay, here's A. And so ultimately, from the beginning, we end up with a vector. So if this is our, kind of our origin, we end up with a vector like this, okay? And that vector is, well, it's A plus B plus F, okay? And what should be clear here is that this guy and this guy are the same. Okay, the directions are pretty much the same. Obviously, the scales aren't perfect. I can't draw perfectly. If I had graph paper, I could do this really nicely. Actually, I should probably look into figuring out how I can get some graph paper on here. But the bottom line is that the order doesn't matter. Okay, so this is associative. This shows that the order doesn't matter. Okay, the order that you add them. Okay, so it's commutative, it's associative, and that's really cool. And this can be done graphically. The last thing that we should note that we want to kind of get into here is writing all this business is annoying, especially if you have a bunch of them. So what we're going to do is we're going to call this vector right here that we drew right there, that is called the resultant. Resultant. Okay, and we want this pretty often, especially when we're talking about forces. So if you had some particle, and you had a whole bunch of forces acting on it, and so you've got like, I don't know, force going this way and one going this way and one going that way, and one pulling in this direction maybe, and another one, I don't know, whatever. Okay, you might want to know what the total of those forces were, and you would add all of those forces. So you would add this force, let's call it force 1, force 2, force 3, force 4, and force 5, and so we would say, F1 plus F2 plus F3 plus F4 plus F5, okay, and I'm not going to do these because I haven't given them any numbers, so I can't really do it. And you're going to add those up, and you get the resultant, which your book uses a bold-faced R. Again, bold because it's a resultant. Because it's a vector. I'm going to use it as an arrow because I can't draw bold. Okay, so the resultant is and remember it's a vector. So it's going to have magnitude and direction. Okay, so that's important, and in a second we're going to kind of we're going to start getting into how mathematically to add these. Okay, because right now I've just done it graphically and not like algebraically. One thing I want to note is that all of these that I drew, all of these vectors that I drew up here, these are all coplanar, meaning that they're all in a single plane, and they're nice and easy to add when they're in one plane. So this is kind of like a 2D plane. Any two vectors are coplanar, but once you get to three vectors, it's highly unlikely that they'll be coplanar, unless you're in a math class or an engineering class, because then obviously we like 2D because it makes our lives easier. But in the real world, of course, things are at all kinds of different funny angles. If they're in 3D, you can still add them. You just end up in three-dimensional space. It's harder for me to draw. Your textbook is going to have some nice drawings of those, and I'm going to lean on the textbook for those images because I'm not going to. I could draw them. They're just not going to be as good. So just kind of be aware that right now we're dealing with coplanar. They may not always be coplanar. So that's important. Okay. Now, back over here to this idea of this resultant. Okay, so one of the things that I want to consider with this resultant is that what the resultant is doing, in essence, is I'm able to take this resultant, its magnitude and direction, and I can ignore all of these. And instead, I can only think about the resultant. So basically, you can replace all of this with this. Okay, and it will have the same effect on the particle. Okay. Now, some of you might be complaining and saying, wait a second, if I look at these forces, okay, and if you look at these forces over here, okay, you might say, well, wait a second, these four are squeezing, Okay, this one's pulling. Okay, so there might be some compression on this thing that we're ignoring. If I replace it and I just said, well, I'm going to, instead of drawing all this nonsense, I'm just going to draw like a particle, and I'm just going to kind of draw a force going off maybe in this direction. Maybe that's the resultant. Okay, so you might say to yourself, wait a second, what about the squeeze? Okay, what about the squeeze that appears to be going on here? Where's my squeeze? Okay, where's my squeeze? Okay, and I'll give you a second to think about that. I'm not going to give you a second. I'm just going to zoom out, okay, to one of the things that I said that, you know, these things are always really interesting when you get really zoomed in. But, oh, son of a, okay, let's go back there, buddy. Okay, let's zoom in over here. Okay, notice here, okay, and this is an important thought, okay? We're dealing with rigid bodies, okay? So the body itself is not going to compress. It's basically not going to feel the force internal, okay? Once you get outside of statics and you start thinking about the deformation of your bridge or things like that, you can get into deformable bodies, okay? And that allows you some more equations. Right now, you know, in statics is kind of interesting. We're going to end up with, for a lot of our problems, we're going to end up with 6 equations, and that's all you have. And that's really cool. That's a lot. And you can solve these 6 equations, but sometimes things get a little bit more complicated, and you have to consider the deformation of the body, okay? And that will be in your future classes. But for now, we're going to treat the bodies as if they're rigid. It's an assumption. It's like when you're in, you know, when you're in physics and they do the projectile problems and they say, assume there's no wind resistance. Of course there's wind resistance. There's always wind resistance. But to learn the material, you think about it as if there's no wind resistance. And or a frictionless pulley. There's always friction in that pulley. There's no such thing as a frictionless pulley. So there's no such thing as a truly rigid body, but we're going to work as if there were. Okay, so let's zoom back out and let's get, oh, I didn't want to do that. Let's hope that that didn't, oh, cool, you can move all of that. All right, oh no, all right, so let's get back over here. So we can replace with the resultant precisely because, okay, we can do that in part because, well, because we're rigid bodies, okay? So we don't have to worry about the squeezing this, okay? All we're worried about is the external effect on, you know, which direction is this thing going to accelerate, okay? That might create issues in fluids and some other things, although, you know, some fluids are considered incompressible. It doesn't matter. We're not doing fluids. Okay, so let's move on. So what this also means, and this is important for addition, is that because, so if I have a resultant, and it's just kind of like a random vector, if I have a vector going off like this, you know, we always go up and to the right. Let's go down and to the right, okay? This is really exciting. Hopefully you got, you know, you've got some energy because this is going to be awesome. We're going down and to the right. Okay, it's like that weird movie with Kevin Costner. Did you see it, JFK? Anyway. We'll just call it, this will be some random resultant, or it could just be a random force. It doesn't have to be R, it could be A. It doesn't matter. Okay, so the nice thing about this is I can take this force, and I can also, if I wanted to, I could say, you know what, I don't want to deal with that force. I want to get the other forces that go into it, okay? And so there's kind of 2 ways you can look at this. You can break this thing apart. So one way you could do it is you could say, well, I want to think about it as this force, okay, and this force, okay? That's a pretty logical way to do it because that would be R in the X direction and R in the Y direction. You could do that. So these would also be vectors, so they would get those little arrows on them, okay? You could also do it this way, okay, because note the order doesn't matter, so I could do RY plus RX, okay? Note I could also do, you know, R is A plus B plus C, okay, plus D plus E, and then F, okay, if you wanted to. Okay, you could do that. Now, I don't really know why you would want to do that, but you could, okay? And what's cool about this is that I could add those vectors, could add this plus this plus this plus this in any order, okay? And what I'm going to get is this, okay? Now, you might say, why would I want to do that? Okay, why would I want to split something nice and clean like this one into a bunch of noise? Well, you probably wouldn't. But there might be times, there'll be lots of times when you'll want to split it up that way, okay? Okay, so in more kind of formal way of looking at it, one of the things that your book, or a sort of type of problem that shows up from time to time, is we've got some force. I'm just going to kind of draw it going off in a random direction. Let's have it going off this way, F. Okay, there's our force. And for some reason or another, we want to split it apart into two components, let's say A and B. And so sometimes you might know, like you might be, it's like, I don't know, somebody's, I'm gonna do two kind of examples here. Okay, and so this will be F, and this will be a different example. Okay, so these are two different possibilities. And so what's going to happen is, somebody says, well, all right, you want to split it up into two components. One component here is going to be A. Okay, what is B? Okay, so to go from A to F, so basically, the question is kind of like, it's almost like an algebra problem, right? The algebra problem is F equals A plus what? Okay, in this case, it needs to be B. Okay, so if we're adding A plus B, then we go to A, and then, this is called tip to tail. This is kind of the formal name for it. We're going to kind of come back tip to tail that way. Okay, so A plus B, tip to tail, as they say. Okay, so in this case, what we're suggesting here is that this is known, and this is unknown. Okay. Now you may sit here and go, well, how in the heck do we do that? Well, let's put some numbers in here to make this a little cleaner, so you can kind of understand what's going on here. Okay, so in this case, and unfortunately I didn't necessarily draw an easy one, but let's suppose that F is, 5, let's just do meters. Okay, let's keep it easy. Okay, why not? Okay, and let's give it an angle here, because we know everything about this one. Okay, and it's acting at 30 degrees, from vertical. Okay, cool. Okay, what about A? Okay, well, A is, we'll just kind of make up a number here. We'll just say it's, 7 meters. Okay, and it's got an angle as well. Okay, let's make this angle. Let's make that 45 degrees. Let's keep these angles simple. Okay, so now we want to know what is B. Okay, so hopefully some part of your brain is now screaming, wait a second. This is a trig problem, and that's exactly what this is. This is a trig problem. So let's zoom in and let's solve some trig, okay? So we're gonna have to zoom in so we can kind of see what's going on here, okay? Okay, let's start with the fact that this angle at the bottom is 75 degrees, and we know that because this portion of the angle is 45 degrees between the vertical and this angle that's going off at 45. So we take those 45 degrees and we add them to these 30, and we get 75 for the whole angle. So we'll go ahead and we're going to use the law of cosines here, which can be written like this. And if we zoom over here, if we stare at that a little bit, we'll note that we know all of these things. The only unusual thing here is that for the side lengths, I had to put magnitude signs over there in order to make them into scalars. So if we plug all this in, so for F, we're going to plug in, or for the magnitude of F, we'll plug in 5 meters. For the magnitude of A, we'll plug in 7 meters. And we'll plug in 5 meters and 7 meters, okay, and the cosine of the angle. And we will end up getting B equals, okay, approximately that many meters. Okay, and then if you're like, okay, well, that's cool, but we also need to know the angle. So we have to figure that angle out. So we're going to use the law of sines, which can be written, something along these lines where, okay, so we've got the sine of 75, okay, which is this angle right here, and then the side across from it, which is B, okay, and then I'm going to do the sine of this angle, okay, because I want to know B's, because I'm trying to get, I've got the magnitude of B, and now I want to get the direction of B, so I want this angle right here, okay, which I'm going to call alpha, so we'll go ahead and put an alpha right there, over F, which is the side across from it. Okay, so again, if for B, I'm going to plug in 7.48. So right here, I'm going to plug in 7.48 meters. And right here, I'm going to plug in 7 meters for F. Okay, and so if we solve that, then alpha equals more or less 64.48 degrees. Okay, this is fewer significant figures than I usually like, but we're going to run with it for the moment. Okay, so then it looks like we're almost all the way there. We've got a magnitude. We've got a direction, but I don't like this direction. We shouldn't use this direction. And the reason we don't like this direction is because what is that angle relative to? Well, it's relative to A, which is 45 degrees off of anything like useful. Okay, and in fact, it looks like I kind of might have drawn this all wrong, right? Because if I'd kind of drawn a little triangle here, okay, if this is 45 degrees, okay, now obviously I've done a poor job drawing this triangle, but this is a right angle then. Okay, this is 45. That means this right here, that's 45 degrees. Okay, which means this angle that defines B is 45 plus 64.48. Okay, so I would call that larger angle, let's call it beta for now. Okay, 45 plus 64.48. So that's 109.48, 109.48 degrees, okay, from the vertical. Okay, so that means I can define B, if I wanted to, as 7.48 meters at an angle. And in this case, I'm going to define it coming off the vertical, going this way, okay, of 109.48 degrees. I would also like you to note that you could also have written this as 7.48, and this would probably be better at, okay, now I'm going to define it coming off of the horizontal. Okay, so I'm going to subtract 90 degrees from that, and I'm going to get 19.48 degrees. Okay, and that's a pretty nice way to do it. You could also do beta equals, I'm not suggesting that you do this, but you could. You could do it, a lot of people like to define everything from the positive x direction, in which case it would be 180 minus 19.48. So in my head, as best my head works, I could get 160.52 degrees, okay, from positive x, and it's still 7.48 meters, okay, okay. And there's a few other ways you could do this. I mean, you could also do, if you really wanted to, you could make it a negative 19.48 degrees going in that direction, but now it's a negative 7.48 meters, okay? In that case, we're defining our vector kind of going this way, but then it's negative, so it kind of goes off that way, 7.48 meters. A lot of times it's very helpful to just kind of draw it, okay? So like I would usually just do this, 7.48 meters, okay? And I'm going to draw usually the smallest angle I can, okay? So it's got to go to one of the four cardinal directions, and I'm going to draw it as 19.48 degrees, okay? And then I should also make a note, I'm never going to give this many significant digits. I'm always going to go to 3, okay? So this number is fine. This number is too precise, 19.5. Okay, that's what I recommend. Okay. So now let's do an alternate problem. I guess I'm going to have to erase a bunch of this. Okay, so in this problem, you're given f, okay? And you're given two other vectors that you want to, so in this one, we'll go back to this one. This one you were given f, and you were given a, okay, and you were looking for b. Okay, so this was the question mark. Okay, and this one, you're given f, and you're going to be given the directions of a and b. So you know that A, for example, maybe you know that A goes in this direction, but you don't know how far it goes. Okay, so you know the direction of A, but we don't know how far it goes. Okay. And let's suppose you know something about B. You know that B goes, I don't know, let's just make the direction, right? It doesn't matter. We know that B goes off in this direction. Okay. Well, so we're going to have to know some things. So let's suppose you know everything about F. So we'll go ahead and, again, I'll draw in some angles for F. Okay, so we'll say that F is going off 30 degrees from vertical. So that's a 30 right there. Okay, that's 30. Okay, now we know that, now we know these angles for A and B. I'm just going to make them off the horizontal. Okay, but obviously you have to be able to do the geometry to get them from other directions. So let's suppose A is at 20 degrees. Okay, and B is at, I don't know, let's go with 15. Okay, so that's all we know. We just know these two things have angles. Okay, so what we need to do then is we need to create a triangle. Okay, once we create a triangle, this is trigonometry. Okay, so there's two possible ways to do this, to create a triangle, and they both involve moving things around. So the one thing we can do is the tip to tail thing. So I can either kind of take this direction, and I want to add this direction, and I need to end up at this point. Okay, so I can kind of basically slide this line in this direction. Okay, until it kind of lines up the way that I want it to. Okay, so that's a parallel line. So here we go. So I've basically slid this line. Now I don't know how long it is, right? Because that's one of the things I'm looking for. So now I've just created a triangle. So here is B, right here. And here is A. Okay, so if I redraw that triangle down here just to make it kind of a little cleaner, here's F. Here's B, and here's A. Okay, and we know some angles, right? We know this angle right here off the horizontal is 15 degrees. We know this one right here is 30, so we know this is 30 degrees. We know this one right here is 15 degrees. And A, which is poorly drawn, is 20 degrees right here. 20 degrees. Okay? So that gives us a triangle, and we just have to start kind of figuring out our angles. Now that's, of course, not our favorite thing to do, but we can do it. Okay, so let's start. I'll kind of start drawing on this with different colors. So this angle, so this whole thing is a right angle. So we've got 90 minus 30 minus 15. Okay, so that's 90 minus 45. So this one's a 45 degree angle. Okay, so we can go up here now, and we've got this triangle right here, and this is 30 degrees, and this is 90 degrees. So that means this one is 60 degrees. Okay, because this triangle right here, okay, it's 30, 60, 90. Okay, so we've got a 60, we've got a 20. So those all have to add up to 180. So this becomes a 100 degree angle. Okay, which means that this angle right here is 100 plus 45. These three have to add up to 180. So this becomes 35 degrees. Okay, yes, I do expect you to be able to figure out this geometry. And if you need help with it, I can create like a triangle help video if you want me to. That would be fine. So this triangle now, if we assume F is the same as it was up here, what did I make it? What was its length? What was the length of F? F was, I don't know why it keeps clicking back to that spot. F was 5 meters. Okay, so if I want the other sides, I know their directions for A and B, but if I want to know their magnitude, then I'm going to use the law of sines in this case. Okay, because F, I know it to be 5 meters. So law of sine. Okay, so it looks something like that. And again, for F, I'm going to plug in a 5. I think we're doing meters for these problems, so we'll plug in 5 meters. And then we just need to solve both of these. So we'll solve this one, and then we'll solve this one. And so we'll get the magnitudes of both of those. Okay, so that gives us the magnitudes. Yes, we plug those guys in, it gives us the magnitudes, and then we have the directions, and we just need to kind of put them in their place, so that B equals 8.58 meters at 15 degrees. Excuse me. My apologies. Okay. Let's do it from this angle. Okay. And we'll say 15 degrees. And A equals 6.16 meters at, and I can make the angle this way if I wanted to, an angle of, what did we decide that was? Oh, 20 degrees. Okay. I guess those were given. More typical for me, you will see, I prefer to use the angles from the positive x direction. That is kind of how I usually do it. But, you know, whatever works for you. So in this case, this would be 200 degrees. Okay. Or this one would be, if you wanted to, I guess it would be 165 degrees. Okay. But, you know, this is perfectly fine. Okay. Last thing that we should note here is that, so that's one way to solve this. The other way you could have solved this, if we went back up to our original thing here, so here's A, we know its direction. Here's B, okay, we know its direction. So what I did in that case is I took A and I shifted it up and to the left until it hit this line. Okay, I also could have shifted B upwards until B had made a different triangle. So you can see there's a different triangle here with A, and here's B, right? So now I've got this triangle, right? Okay. Okay, so if I were to draw that triangle, it's basically the same triangle as this triangle, okay? It just, so let's see if it looks like this, and that, okay? And this is B, and this is A, and this is F. Okay, and if you do the law of sines, and if you do the law of sines on that, you're going to end up with basically the same equations as you get here, and you're going to end up with the exact same answers. Okay, what I just did here by moving it in kind of two different directions creates a parallelogram. So this is the force that matters, and then around it is a parallelogram. So they call it, I think this has some fancy name like the law of parallelograms or whatever. But basically it says that, you know, you can add A to B to get F, or you can add B to A to get F. Okay, so I mean you can kind of do this in whatever order you want, okay, and you're going to get there. Okay, or I always prefer head to tail. Okay, so the head of one arrow right here goes to the tail of the other one. Okay, the head of this one goes to the tail of that one. Okay, and then we go that way. Okay, so that's all I got for this evening. Again, take care of yourselves, and let me know if I can help in any way. I think this is really just going to be the A part of this lecture. Look at that, how far we moved. Because there are lots of different ways to do some mathematical operations on vectors, and, you know, we're just kind of starting. So don't forget Newton's laws. Don't forget vectors and scalars. And, you know, we're just going to keep working on adding these things. And that's it. So hope you all are having a good night or day or morning. I guess this will be up in the morning. And that's it. So see you guys. All right. Bye.